Good morning. We will continue with soda ash. And last time we had discussed the Leblanc process. I also mentioned to you that it was a tragedy for Leblanc that he had to commit suicide because of various reasons. And also that the Leblanc process was of historical significance, not only because it was the first such process that was developed for soda ash. This kind of a process was something unimaginable. The second thing was that this actually gave, in some sense, birth to many associated things around chemical technology and chemical engineering. So it was very, very significant. The person who has been credited with a lot of what was achieved in the Leblanc process is George Davis. He was actually a factory inspector, and more specifically, he was the alkali inspector. Alkali means at that time we are talking about the Leblanc process. That's what he was inspecting because a large number of plants had started coming out. It was Davis who realized how polluting this Leblanc process is, and it was his interventions that really led to the first Factories Act, the Alkali Act, the Industrial Act on Alkali. It was basically because of people like George Davis. It was based on his recommendations that it was said that all such soda ash manufacturers must be able to recover at least 95% of the HCl which is coming out. It's become very fashionable to talk about green chemistry, green technology, as if these guys today have for the first time discovered these things. Or rubbish. There were people like George Davis who enunciated this principle long, long ago in the 19th century. Look what he says. You can see how visionary he was. So George Davis was a pioneer of sustainability. His years as alkali inspector and his abhorrence of the extremely wasteful and polluting Leblanc process, which in its early forms produced copious amounts of hydrochloric acid and sulfur waste, shine through when he extols. The aim of all chemical procedures should be the utilization of everything and the avoidance of waste. It is often cheaper to prevent waste than to attempt to utilize a waste product. See how visionary he was. And it's true, many of these byproducts of the Leblanc process were value added and one could utilize them. But I think the point that he was trying to make is that if you didn't form them in the first place, that would be the best. And it is because of this kind of remarkable farsightedness that he is actually considered to be one of the chemical engineers who changed the world. That's how great he was. It's also very instructive. I mean, like all of you, you've taken admission in chemical engineering. Remember that this discipline did not always exist. I think it's very important that you know that. Davis is the person who wrote the seminal book, A Handbook of Chemical Engineering, which was published in 1991. It was like a Bible for all chemical engineers. In this, he's also tried to articulate what he saw as the attributes and functions of a chemical engineer. And he says, in this handbook, he defines the attributes and functions of the chemical engineer and makes a compelling case for why chemical engineering should be considered a standalone discipline, separate from applied chemistry, chemical technology, or the person who at the time most commonly filled the role we now reserve for the chemical engineer, which is the mechanical engineer with a little knowledge of chemistry. I think you need to really understand that where we are coming from, that it was not something that was so obvious because all of equipment and scale up, etc., was considered to be the domain of mechanical engineers. They are the ones who fabricated things. They required the inputs of people in chemistry, and so that's how they were working. It was George Davis who was the one who enunciated for the first time the importance of chemical engineering as a separate branch. So I think all of you owe a lot of respect to George Davis. And let me tell you that all these things that people talk about, like green technology, etc., were actually thought of and practiced by him long, long ago. This is not a new subject for sure. Let us come back to the Leblanc process, and although we defined it in bits and pieces, let's just go through the process in a bit of detail. What we saw was that it's really the reaction of converting first of sodium chloride into sodium sulfate. That's basically what it is. Now this reaction is done in two steps, where NaCl first is converted into NaHSO4, and then you add more NaCl and convert it into Na2SO4. And of course, in both steps, you will have the release of HCl. Can any of you tell me why this had to be done in two steps? Why wasn't it done in one step? And by the way, this is the kind of thing I want you to do everywhere. Everywhere, keep asking, why did this? How? Why? Because that's how you make a subject interesting. I should question, why should I do it? If I could do it in a single step, I'll do it.
To ensure maximum conversion.
That's a wonderful answer, but it's too general, and you're absolutely right. Ultimately, that's true what you're saying. But why? How do I ensure maximum conversion by doing it in two steps?
Sir, by maintaining the temperature in various stages.
I mean, maintaining means you're saying you have to maintain different temperatures. Is that what you're trying to say?
Yes, sir.
Yeah, and why would that be? That's very good.
Sir, because the conversion rate for different reactions will be different at different temperatures.
I mean, that's brilliant. But from a thermodynamic perspective, what are you trying to say? Both of what you said is actually right. But I just want it to be, your answer should be very, very crisp.
Sir, to prevent any NaHSO4 going further in the process.
NaHSO4 going further in the process means?
Sir, so that the NaHSO4 is completely converted to Na2SO4.
Yeah, how do I do that? Because by putting it in two reactors.
Sir, so that any Na2 after the second reaction only Na2SO4 will go ahead.
Correct.
But if it is done in one step, NaHSO4 may also go ahead in the next reaction.
Yeah, what you're saying is that it will remain unreacted, right?
Sir, it's because of the HCl probably.
Yeah, what about HCl?
Sir, the equilibrium, because both the steps generate HCl, and if we don't do it in like two steps, the first step will generate HCl and the second step won't be able to happen because HCl is already there. So the equilibrium for the second step
HCl,
would not shift forward.
HCl is a gas. It can come out.
Okay.
It should. Why should it sit around there?
Sir, NaHSO4 is kind of an intermediate which is formed.
Yes, you can think of it as an intermediate, but it's a stable intermediate. Sodium bisulfite, sulfate is a product. You can buy it.
Yes.
What happens is that this first step is an exothermic reaction. Okay, this step. And the second step is an endothermic reaction. So what happens is that if I put the two together, I'll have a problem. You won't know how to optimize what? Because if you heat up, if you have a high temperature, then exactly as one of you said, NaHSO4 may not form completely. But the reason for that is thermodynamics. Your answer should be a little more focused. You're giving intuitive answers. Just try to be a bit more focused and take your answers to the logical explanations. Is that clear to everyone? Why you do it in two steps?
Yes, sir.
Okay. In both the steps, of course, you generate HCl, and exactly like it was taught before that you spray water and end up forming HCl solution. Or you could even, if you did not spray water, suppose you had a means of taking the gas phase HCl and directly doing a conversion. And we'll talk about such things. That's one. Second, although this Leblanc process, we are talking about having been invented way back in the 18th century. I've seen things even in the 60s, more as a research, not so much as a practicing technology, because the Leblanc process is obsolete today. But something very interesting where because you have to otherwise mix these solids, and mixing solids is always a complicated problem in many cases. What people have done is that they have actually made molten NaCl and then carried out reactions where I melt the NaCl, this NaCl for example, and into that I add the sodium bisulfate, and that improves the kinetics greatly and the completeness of the reaction. So there are many innovations that you can do even today. So after that, once you have got sodium sulfate, the salt cake, then of course second part, which is that you put limestone and coke, and this has to be all heated up nicely, mixed in a rotary furnace, and that's the step. It's broken up into two steps, but at the end of it you get sodium carbonate and calcium sulfide, black ash. Now this is the one that is crushed and then it's leached with water. After leaching with water, you get the sodium carbonate coming out, and the calcium sulfide is separated out. It's very interesting that when they do this, they also introduce some hot gases, the flue gases from here. Some of that is introduced here. Can anyone tell me why possibly they would be introducing the hot gases? One, of course, would be to supply the heat for evaporating and things like that. I mean, that's one reason. Any other reason that might be there for that?
Sir, the CO2 present in the flue gas may react to form Na2CO3.
Yeah, it will form with what? Very good.
Na2S.
You are, no, not with Na2S. What will happen is that when you are heating, because these things are at fairly high temperatures, so some of the sodium carbonate may actually decompose to sodium oxide and CO2. And so by introducing the flue gases later on, maybe that part of the sodium oxide, the sodium hydroxide or oxide, whatever you call it, will react with the CO2, and it will basically help to increase the amount of sodium carbonate. Is that clear?
Yes, sir.
And then after that, what you do is that you have to concentrate it so that you can take out the sodium carbonate as crystals. So it's a evaporative crystallization, and so that's what they're doing in an open pan evaporator, for which you require water. Okay. And finally, it goes through a calcination step over here, and you get your sodium carbonate. Can anyone tell me why a calcination was required here?
So to consume all the unreacted carbon.
Oh, you're saying if there is any carbon which is present, but the carbon will show up in the black ash. After I do the leaching, if there were any insolubles, those will come along with my calcium sulfide. Isn't it?
Yes, sir.
So why would I do a calcination?
Or drying it, like we don't get the hydrated salt, and we get
Brilliant, brilliant, brilliant. Very nice. So what happens is that when you are doing this open pan evaporation, you actually get the sodium carbonate decahydrate. You can imagine 10 molecules of water. If you have to transport, for example, you'd be transporting so much of water. So what you therefore do is that you by the calcination, you are able to remove those waters of crystallization, and so that you get an anhydrous form of sodium carbonate. What you must do as chemical engineers is please have a look at each and every unit operation and ask yourself, why are we doing it? And that is really what will get the best out of you. And you can see that some of it is of course obvious, and some of it you have to think a bit. It's not exactly obvious. Obviously, the subject gets much more interesting. when you do that. This is a concept which has become quite popular, and so I thought that I'll mention to you. This is known as the E factor. E is like the environmental factor. The definition is that you carry out a process and you see what is the kilograms of waste that you're forming in the process divided by the kilogram of product. So, for example, if I was making sodium carbonate by the Leblanc process, this data is available. 1000 kg means 1 ton of sodium carbonate. Let's assume 98% yield is okay. Keep that as 1 ton. And then for this, I need 1126 kg, 1.126 ton of sodium chloride, which was the main feedstock, and sulfuric acid. That's what we are adding, 945 kg. And then I needed limestone, 963 kg, and coke, 463 kg. If I add it all up, that comes to 3.497 tons. And what did I get out of it? I effectively got 1 ton of sodium carbonate. So my waste is 2.497 tons. So my E factor is equal to 2.497 divided by 1 is equal to 2.497. Now let us look at the subsequent innovations. It's too bad that Leblanc was not alive when all these great things were done on his process. The first was people said, great, you have recovered HCl, you sprayed it with water and got HCl. And then people said, yes, but what am I supposed to do with this HCl? Someone had the smart idea, hey, why don't we convert it into chlorine? We discussed when we were talking about the textile industry, how important bleaching was and the role of chlorine. That chlorine had already been identified as a very promising bleaching agent and bleaching powder after the reaction of chlorine with lime. So, people started developing technologies to convert HCl into chlorine. Again, I must tell you, all of these are need-based things. They're need-based. There was a genuine need for a solution. And that's when you find a good solution. Otherwise, developing processes for the heck of it, which nobody will ever use, what's the point? So that's what they did. Now, and you can also see the evolution of technology. So the first technology that was developed was the oxidation of HCl with manganese dioxide. It was a good process in the sense that it was a fairly low temperature process, and it gave manganese chloride. It was a stoichiometric requirement of manganese dioxide. So it gave manganese chloride, and plus it gave chlorine, and the H from here and the O from here, that basically formed 2 molecules of water. This was known as the well-done process. Later on, what they realized is, again, you'll have to regenerate the MnO2 from MnCl2. That's again going to be an involved process, which means that again I'll have to add some alkali to it, convert it into manganese hydroxide, then oxidize it and get MnO2. So again, you'll see it's very wasteful. A lot of chemicals will be required. So at that time, this person Deacon had the smart idea that why don't we explore the oxidation of HCl with air? Why not oxygen from air as an oxidizing agent? And that's the kind of thing you have to ask. And of course, people knew that yes, you might be able to do it, but probably at a higher temperature. But someone would have said that, "ठीक है, we have to do it at a higher temperature, but maybe that is much better than trying to regenerate MnO2 from MnCl2." And so this was a very elegant process that was developed, known as the Deacon process, HCl and oxygen, and one of the earliest catalytic systems, copper chloride, temperature of 450 to 460 degrees centigrade, and you get chlorine. This is a very nice situation. You can see if I'm doing it at 450, 460 degrees centigrade, obviously I'm doing a gas phase reaction. Now, if I'm going to do a gas phase reaction, why should I put water over here and make HCl? I would much rather try to see. And remember, this is at a very high temperature, 700, 800 degrees centigrade, maybe even 1000 degrees centigrade, when this reaction is being carried out. So I'll be getting gaseous HCl. So why would I again put it in water and make a solution of HCl and again strip off and make HCl gas when I've got hot HCl coming out? I'm not very sure if the decant process is done that way, but certainly if you were doing your home paper and you have to work on it, then obviously you should do it directly from the gas phase as it is coming out from here. Now this was a brilliant invention, this conversion of HCl into chlorine, because it solved one of the most major problems you have seen. How much of sulfuric acid was being used and how much of HCl was being produced, stoichiometric quantity. And that much of chlorine if you can get, okay, I mean that's huge, okay. And those were the days before the caustic soda chlorine process was born. So this was one of the best processes for making chlorine. Another person, Chance, had a brilliant idea and he said, hey, this calcium sulfide, why don't we try and recover sulfur from it? One is, of course, calcium sulfide when it is interacting with HCl, and especially if you introduce carbon dioxide, the flue gas, it will form calcium carbonate and H2S, which is not bad. So this is one process for making H2S. But also there were variants of this theme, but some and substances that all of them ultimately gave you H2S and calcium carbonate. Now look at the brilliance of this process. Calcium carbonate, I need here limestone, and I've got H2S, and now we've studied the Claus process. A variant of the Claus process probably as it existed at that time, we know that H2S can be converted into sulfur. And you know why Leblanc committed suicide? He could not get sulfuric acid, and that's because sulfur was being utilized for making sulfuric acid for weapons, and because the production of sulfuric acid required chili saltpeter, that also was not available. So the chamber process was active at that time. There was no contact process there. So Leblanc was in disarray. And look at this. I mean, these people said, after all, sodium carbonate does not have any sulfur. So I should be able to recover my sulfuric acid from here. Then I'm not dependent on anyone. I can make my own sulfuric acid. So again, a great invention. By the way, because of this, obviously, when I'm talking about E factor, it would be very interesting to look at the E factor, where now what I do is that what are my products? My products are chlorine. My product is sulfuric acid, which goes back into the process. So I need not take it as a raw material anymore. I can recycle it and stuff like that. So if I compute my E factor, it will change. All right, is that clear to everyone?
Yes, sir.
Because what was my waste is now my product. Now, what is very interesting is that even though these remarkable inventions were made, and look, it was made what? It was made about 100 years or maybe longer, 100, maybe 20 years or thereabouts after Leblanc process was invented. What happened was that the Solvay process started making inroads. When the Solvay plant started coming up, believe it or not, the soda ash price fell by a factor of 2, but that could have been a tactical ploy. It may not have been that that was the cost of production, but they were trying to gain market share, that particular process. And maybe, you know, sometimes people do that and then other companies go bust. These Leblanc guys felt threatened by the Solvay process because there were many advantages to the Solvay process. There are disadvantages also, okay, but there were advantages. And so the Leblanc people were absolutely on the back foot. And as a last desperate means, what these Leblanc manufacturers did was that they formed a cartel which was called United Alkali. And in 1926, they merged with Imperial Chemical Industries, ICI. That's where Trevor Kletz was. You know, we saw Trevor Kletz one of the greatest chemical engineers from safety point of view. I was myself very fortunate to work in this company for many years. They did this, but it really did not save them, because finally the Solvay process became dominant. I think by the 40s, early 40s, the Leblanc process had more or less come to an end. We've got chlorine, we've got calcium carbonate coming back, we've got the sulfuric acid back. So I don't need this sulfuric acid again over here. I mean, of course, I need it in the sense that obviously I have to produce sulfuric acid and do the Leblanc process, but my sulfur source is coming from within. Limestone I'm getting back. So many good things. But even then it struggled and lost ground. Why? What was the problem? Or what may have been the problem which you can think of?
Sir, the amount of steps.
Very good. Let's put it down. I'll put students. Amount of steps. Okay. Anything else?
So capital required was more to recycle the waste. Yes, sir.
Capital required was more, and waste recovery was more involved process. Huh?
Yes, sir.
And waste recovery was an involved process.
So a low atom economy.
Low atom economy. Of course, with the recycle of all the waste, the atom economy was not so bad. Correct? But yes, we'll put it down. You're actually right. Anything else?
Power requirement.
Very good. There is power requirement to run the rotary calciner and things like that. But it was more of thermal energy requirement. Okay? But I think you've made a very important point that we can say overall energy requirement was very high. Is that right? Is that
Yes.
what you're trying to say?
Yes, sir.
Energy requirement was very high. Anything else?
Sir, it was dependent on some other process for its raw materials.
Okay. Had a dependence on other processes for raw materials. Like which ones?
So sulfuric acid, sir.
Yeah, but sulfuric acid later on they were getting from within,
Oh,
isn't it?
yes, sir.
Okay, but anyway, we'll put it down. Maybe some people were and some people weren't. I want you to look at it now from a chemical engineer's perspective.
Sir, too many steps.
Too many steps?
Yes, maybe the Solvay process has fewer steps.
Okay, let's put too many steps. Okay, what else? Maybe this too many steps, let's qualify it. You see, the Leblanc process was a batch process. Because of the batch process, too much labor requirement, and any batch process, batch to batch variations, and the other is, you see that H2S problem did not go away completely. Safety issues are there, right?
Yes, sir. Yes, sir.
What was not taken care of was that it is a batch process. There were batch to batch variations. There are still safety issues. So these were things that the Leblanc process could not handle.
So, like previously you had mentioned, the solid-solid interaction was also very tough,
Yes,
and by the
yes,
time
very
it was
good.
not.
Mixing of solids, always an issue, even with rotary furnace. Okay, this is what led to the Solvay process. But remember that it is not, Solvay process was independently invented, and Solvay process made its inroads. It is not that only because of this reason the Solvay process came up. Solvay process actually came up because of certain observations which were made, okay, by certain very famous scientists. And so we will look at that. Solvay was so famous, and the Solvay process was so famous that Solvay used to hold a conference which was called the Solvay conference. And I'm showing the photo from 1927. Look at the people who are there: Albert Einstein, Marie Curie. This is Solvay, and all the people whose names you know: Schrodinger, quantum mechanics, Heisenberg, Niels Bohr, Max Born, Dirac, Bragg, all of them were there. By the way, from this you'll be able to figure out who is who. In fact, this person, Picard, whose name is there right of the left at the back. In fact, Picard was the one who, for the first time in a hot air balloon, he went to the stratosphere. Picard was probably more famous than Einstein or any of these guys. I mean, it's interesting, and all that was funded by Solvay. So Solvay was so visionary. They made a lot of money and they spent a lot of money. And this Picard's grandson ran the first plane which was run only on solar energy. There was not a gram of any fuel there. And I was very lucky to get an invite to see this plane when it came to Ahmedabad in 2015, and and even talked to the pilots there. Solvay was one of the sponsors of this particular plane, the Solar Impulse, which flew round the world for the first time without a gram of fuel. During the daytime, it would go up above the clouds so that there's no cloud, and they would continuously get the sunshine. The entire wingspan was all solar photovoltaics. During the night, it would come down. Come down means at a lower level, and it would be run on the battery. And it's all lithium-ion battery. And there's only room for one person to sit here. So only one pilot, that's it. All that you can imagine was linked to the aura of the Solvay process. So what is the Solvay process, which all of us know very well? Effectively, if you write the overall reaction, you can write it as sodium chloride plus calcium carbonate going to sodium carbonate plus calcium chloride. Except that this reaction will never go on its own, because the delta G is positive, delta H is also positive. So it doesn't go, and you can say, yeah, but actually it makes use of ammonia. Yes, it makes use of ammonia. You can think of ammonia as a catalyst. But ammonia is not making the delta G negative for this reaction, because the ammonia is getting recycled. It's a catalyst. It's not really affecting the overall thermodynamics. Can anyone tell me how the thermodynamics of this reaction might be getting favored, the overall thermodynamics?
So by increasing the temperature.
How would you increase the temperature?
So insulated pressurized heating.
Heating. So any heating means that there will be an energy input, right?
There will be an energy input, but we need to ensure that it is not an open system. It should be a closed system.
Yeah.
Otherwise, the calcium carbonate would decompose and the CO2 would be vented off.
Right. So what do you want to do? You want a closed system for the calcination of calcium carbonate.
Yes, sir. So it
Brilliant.
will be an equilibrium.
So can we use the same like introduction of flue gases? Because that will also heat the process up, plus Na2CO3 can get decomposed again.
Right. Okay. When I've shown you that equation, I've not assumed any losses. I'm just showing you the thermodynamic values, right?
So we can remove the calcium chloride continuously so as to increase the equilibrium on the right hand side.
So you think that this is a one-step process like this?
No, sir.
You'll find out that the calcium chloride actually happens in a separate process. Your idea is good, of trying to push the equilibrium to the right by taking out calcium chloride, but you have to remember that the reaction doesn't quite go as per this whatever simplistic equation that is being shown.
So can we use another solvent except for water?
Yeah, and then what will happen?
So because some salts, for example, if we use ethanol instead of water,
Right.
so NaCl will not be soluble, but
Right.
CaCl2 will be soluble. So that will remain in solution, and the other products may just precipitate out.
Oh, so you are saying that you want to drive this equilibrium forward. You all are coming up with some suggestions which honestly I have not thought of. I thought it's a good idea. What you're saying is use non-water solvent, okay? Solvent such that uh, 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 calcium chloride will dissolve in it and can be removed, right? That's what you're trying to say.
Yes, sir.
To drive the equilibrium forward. Okay? And this assumes that the reaction proceeds as per the equation shown. Correct?
Yes, sir.
That fundamental assumption is not correct, that it proceeds as per the equation shown. It proceeds in a highly convoluted manner. That's the first thing. What actually drives the reaction in this case is, if you show the delta G for a particular reaction, yeah, the delta G is positive. But when I, let's say, like Leblanc, he also carried out a reaction which is thermodynamically unfavorable. How did he do that? He basically provided an energy input from outside. What was that energy input? Coal. He burnt carbon, right? So similarly, over here, if I were to write down all the individual steps that occurred in the Solvay process, what are we talking about? Calcium carbonate has to go to lime plus carbon dioxide. It's a delta H is positive. That's the first step. Delta G is also positive. So obviously, when I'm calcining something, okay, how am I doing it? I'm providing an energy for input. And what is that energy input? I'm burning coal. I'm getting heat. I'm getting high temperature. And so I am able to decompose my calcium carbonate. So moment I couple two reactions, I am okay. I can drive a unfavorable reaction forward by coupling it with another reaction. At the heart of this Solvay process, or one of the most important steps, is that this calcium carbonate doesn't just react with sodium chloride. You have to first decompose it to lime plus carbon dioxide. I think one of you already said that. Okay? But that is not a thermodynamically favorable process. You can see delta H is 43.4 kilocalorie and delta G is also positive for this reaction. So to decompose it, I have to provide sufficient amount of temperature to decompose it, and which means that I have to provide an external energy input. Where is that external energy input coming from? I am mixing, let's say for example, calcium carbonate plus coal. And now I'm heating it up and my coal is forming carbon dioxide. You can see delta H is minus 96.5 kilocalorie. So by coupling the decomposition of calcium carbonate with the burning of coal, my overall thermodynamics becomes favorable. Is it clear?
Yes, sir.
So it's all about the overall thermodynamics, and there are ways of making the overall thermodynamics of a process favorable. But there is no free lunch. You have to obviously supply energy from somewhere. If you were to look at the processes, calcium carbonate has to become lime and carbon dioxide. That is done by burning coal and deriving the heat for that. Then these are all processes that take place later on. What you have is sodium chloride is then reacted along with ammonia and carbon dioxide. That is what gets converted into ammonium carbonate and bicarbonate. There are equilibria that take place over here, and from that sodium bicarbonate will precipitate out. And once you get the sodium bicarbonate, along with that you get ammonium chloride. The ammonium chloride is reacted with the lime formed over here, the slaked lime, and that releases back the ammonia, which is recycled in the process, and you get calcium chloride plus water. This calcium chloride is a waste, whereas actually in the Leblanc process, we could recover all the calcium waste. In the Solvay process, this calcium chloride is a stoichiometric quantity of waste. No one talks about it. It's a pretty bad process in that sense. There's nothing so great about it. Once you get the sodium bicarbonate, you can heat sodium bicarbonate and it gives you sodium carbonate plus carbon dioxide, which gets recycled in the process. Now, if you add up all the delta H values, what you'll find is that the overall delta H becomes negative for this process. Now, the other very interesting thing is that sodium carbonate you can also react with lime, and you can drive the equilibrium to the right and form sodium hydroxide. So people knew that sodium carbonate can be causticized. You can make sodium hydroxide from sodium carbonate. So that was again another very important thing that I should mention. Now, let me tell you that the first surprise is that the Solvay process was not invented by Solvay. The person who made the most important observation around the Solvay process, which is at the heart of the Solvay process, was a physicist, and it was Fresnel. He's also well known for many of the lenses that he had made, Fresnel lenses. This is another thing. In those days, people like to work on interesting problems. They were not so snobbish about, hey, I am a physicist, you are an engineer, I am a chemist, you are this, you are that. And they worked together many times. What did Fresnel do? Fresnel was the person who for the first time discovered that if you take carbon dioxide and ammonia and brine, which is the most important part of the Solvay process, that sodium bicarbonate precipitates out. And this is at the heart of the Solvay process. If this had not happened, there would be no Solvay process. And look, it was very, very early, 1811, that it was reported. Long before the Solvay process as practiced by Solvay came into play. Not only that, there was also a British patent in 1834 granted to these two gentlemen, Dyan and Henning, effectively talking about the Solvay process. So Solvay's feat actually was that he really overcame some of the most important engineering challenges in this process, which led to a practical process. That's what Solvay made his money from, and that's why he's so great, he and his company. You have to look at some of the most important things when we talk about the Solvay process. One thing which I think most of you know is that sodium chloride has a remarkable property that its solubility does not change with temperature. You can see more or less the same solubility at 0 degrees centigrade and 30 degrees centigrade. Ammonium bicarbonate, ammonium chloride, which are all formed in this reaction. You're forming ammonium chloride, you're forming ammonium bicarbonate, all of this stuff, which are intermediates which are formed, their solubility increases with temperature. And you can also see the absolute solubility of these things. And even sodium carbonate has a high solubility. But compared to all of them, the sodium bicarbonate has relatively much lower solubility. And this is what leads to the precipitation of sodium bicarbonate, baking soda, as an intermediate in the Solvay process. Baking soda, of course, in itself is also a product, very important product. Had this solubility criteria not been there, there would be no Solvay process. Now, the other thing that you need to remember is very important is that you look at the various pHs and the constituents. If you have got carbon dioxide in a pH around here, it will be predominantly carbon dioxide. When you are coming at a pH of around here, it will be mostly in the form of bicarbonate, and when you are going to a higher pH, it will be in the form of carbonate. You'll be able to appreciate this when we actually go through the process flow diagram for the Solvay process. But bear this in mind. Now, what I'm going to do is that I will digress for some time and talk about sodium chloride, which is the most important raw material. It is, of course, it was there in the Leblanc process also, but criticality of the purity of sodium chloride was not so important in the Leblanc process, whereas in the Solvay process, you need to use a fairly pure salt and a fairly pure brine derived from the salt. If you don't, then some of these other things that you add can interfere with the process. So that's very important. Another is, today India is one of the largest manufacturers of soda ash in the world. There are plants which are producing more than 1 million tons per annum. And in India, all the sodium chloride is produced from seawater, okay? Or variants, some brines, maybe like subsoil brine or lake brine, okay? But they're all brines. And that's where we get our salt from, and the majority is from seawater. Now, so it's important to understand what is there in seawater and how do I get a pure sodium chloride out of seawater. Intuitively, of course, but I think we just need to run through a bit of the details and also look at some of the complexities. And some of these things will become crucial when we are discussing some of the more recent innovations around the process. So this is seawater. Now, firstly, let me tell you, all the people who produce salt, they don't talk in terms of specific gravity. They talk in terms of a unit known as Baume. The density of seawater is expressed, and brines is expressed by Baume, and Baume is related to specific gravity by this equation. The Baume scale is important because roughly there is a relationship between the amount of the Baume and how much of sodium chloride there is. So typically seawater has about something like 30 grams per liter or 3% of sodium chloride roughly. And so you can see 3.5 Baume is the density as per the Baume meter. Whereas you told someone, it has got a specific gravity of 1.02 something, they can't relate to anything. So that's the importance of the Baume scale. Another thing that I want you to know is that seawater has many different constituents. Of course, of that, the most important is sodium chloride. In fact, if you add up the sodium and the chloride here, you'll come to close to about 30 grams per liter. But it has got sulfate, it has got magnesium, calcium, potassium, carbonate. These things will have to be removed from the salt, which you've got. If these things are going to be hanging around there, then it will interfere with the Solvay process. There's another thing that I want you to do. Make a note of this, that the calcium concentration and the sulfate concentration in terms of grams per liter is 0.43 and 2.74. But this again does not give a field to chemical engineers and chemists into chemistry. Chemistry is based on stoichiometry. That is based on molar understanding. It's not based on so many grams per liter. So if you were to look at what is the molar concentration that we are talking about of these things, you are talking about 0.011 molar of calcium ions, and you are talking about 0.029 molar of sulfate ion, roughly about 3 times. Now this is very important, and we will discuss this as we go along. And so whenever you see these compositions, just convert it into molar compositions. As you are changing density, which is what will happen as I evaporate seawater. Okay? So obviously my seawater will get more concentrated in salts. This is how the Bombay will change, and in turn, because of the changes in Bombay, there will also be changes in the concentrations of all these constituents. So that's basically what is happening. And you'll also see, like, there was some carbonate here, but by the time you have come here, it's not there. Obviously, this is again something that you need to know. The way salt is produced, okay, is through fractional crystallization. That's what you do. Except that you don't do it in a factory. You do it in open fields. You can see these are the initial stream of sea brine. It will fill up into reservoirs. So these are reservoirs. And from this, they will basically start going this way, that way. It will come here, it will go down, it will go into another pan. From there, it will go to another pan. From there to another pan. And finally here, there will be the salt crystallizations that will take place. And then you will also be left with the mother liquor. All of the other impurities, etc., basically get contained in this mother liquor known as bittern. Okay, and these are your salt heaps, which you'll get. These are the salt heaps that you see. Why are we doing all this? We're doing it because the solubility products of these things that can come out when you are evaporating seawater are different. Of course, sodium chloride is a soluble salt, but you take gypsum, it's a sparingly soluble salt. This is the solubility product. Magnesium carbonate, less soluble than gypsum. Calcium carbonate, still less soluble than magnesium carbonate, but comparable. Obviously, what will happen is that when you're evaporating, these will be the things that will come out first. Of course, it will also depend on what is the concentrations of these things that is present. If the concentrations are less than the solubility product, then of course it will remain in soluble state, as it happens in seawater. You'll get a crystal clear seawater, but there's no magnesium carbonate you see over there. No, you don't see gypsum, you don't see calcium carbonate, even though those constituents are there. Another thing that you need to make a note of, that I have seen that, and this is a really serious problem, it's a mindset problem. I find that most engineers are too focused on these so-called very conventional industries, where you have got 5K reactors and this and that, impeller, all that stuff. But I mean, the truth of the matter is, in India, we produce 35 million tons of salt in the open fields. Does it mean that there's no engineering that is required in this? Of course, you require engineering, and you have to figure out what are the best ways of producing salt in the open fields. And why do you do it in the open fields? Why do you do it in the open fields and not in a factory? What is the reason?
Sir, it is cheaper.
Why is it cheaper?
So because you only require the energy of the sun.
Absolutely. You only draw the energy of the sun. And in fact, it's also very interesting that, like, by the time, I'll show you, by the time you come to things like bittern, it is so saline that most of your reactor vessels will start corroding. Whereas you find that the natural reactor, which is the salt pan, doesn't have all these problems of corrosion, which will be very serious problems if you were to do it in a factory in a closed vessel. So bear that in mind. Now, the other very, very important thing to note, and why I want you all to be very, very conscious about technologies meant for the masses, is that in our country, even today, The majority of the salt is produced by salt workers, who are very poor laborers. You can see all these women making salt. If you can give them the best technology to make salt, they'll make more money. And if your technology is not good enough and you produce less amount of salt or less pure salt, they will get less money, but they're putting in the same amount of effort. So it's vitally important that we understand this. It's also very important that we understand that even in things like this, there are major health issues. Like for example, these pans, and when salt, etc., some things are coming out, they need to be raked. They're raked frequently. Okay, and all these women have to go into these pans. Many times they go with their bare feet. Okay, and you can imagine a very saline, salty environment. It corrodes their skin because it's salt, and you know that salt can increase blood pressure. That's why people are advised not to consume salt. When you are constantly working in these places, many of these people tend to get high BP problems because salt tends to dehydrate you. They suffer from dehydration, and because there is such extreme sunshine, and on top of that, salt is white and it reflects light, and you have a very high ultraviolet radiation component, so it can damage your eyes if you're not careful. These are also issues that when you're studying environmental engineering, look at also safety and health aspects of the workers, and not only people in these formal factories. I want you to think about people like them and how you can help them. Is it clear?
Yes, sir.
Okay. Now, the other thing that you need to understand is that when you're going from here to the right and the brine is evaporating, what will happen to the evaporation rate? Will it remain the same?
So please could you repeat the question?
No, I'm just asking, like here you've got 3.5 degree Bombay seawater, and when I'm going here, my brine is getting more and more concentrated till, of course, then the salts will start coming out. I'm asking you that what will happen to the rate of evaporation?
So it will decrease.
It will decrease. And why will it decrease? What controls the rate of evaporation?
So energy provided by the sun.
Right. That's one. As I'm moving to the right, and my concentration of salts is building up, so what will happen is that the water activity will keep dropping, right?
Yes, sir.
What is the water activity of pure water? 1. And as you are getting it more and more concentrated, the water activity will keep coming down, and therefore the vapor pressure will come down, and therefore it gets harder and harder to evaporate. It's much easier here than here. Keep that in mind. The second thing is that if you follow this, what you'll see is, like we saw from the KSP values, initially your calcium carbonate will start precipitating out, maybe followed by magnesium carbonate, because we found that carbonate, calcium, magnesium are all present in your seawater. So if the solubility product gets exceeded, those things will come out. Next to come out will be gypsum. Why? Because there is a large amount of sulfate and calcium in seawater. So you'll get gypsum coming out. And gradually, what you're trying to do is take out those impurities. And the next to come out will be sodium chloride. And the other salts, which will get very concentrated, will be things like magnesium chloride, which are highly soluble salts. That's how you end up doing a fractional crystallization, and I'll get relatively pure sodium chloride coming out with all the soluble impurities on the right side in the bittern and all the less soluble impurities on the left side, which came out before the crystallization of NaCl. All clear?
Yes, sir.
Okay. So let us look a bit more at the details. This is just showing it. Obviously, in a brine is always present as iron, but I could write equivalent salt concentration: calcium sulfate, magnesium chloride, sodium chloride, potassium chloride, sodium bromide, and water. Let's say if I start with seawater, which is about 3.5 degree Bombay. You must also remember that every part of India does not have 3.5 degree Bombay. The eastern part of India, there are many rivers that flow into the sea. Okay? So what happens is the rivers are basically freshwater bodies, and so near the coastal areas of those eastern places, what you'll have is a lower Bombay, a lower salt concentration, whereas in places like Gujarat, it will be closer to 3.5%. Okay? Uh, and that's what you have as your compositions. You can see, like say, suppose I start at 2.84 Bombay with something like 1342 liters, then at 3.50, it's 1103 liters of solution. And obviously the difference will be the amount of water that is evaporating. Then as I go here, this point is basically the point where I have the onset of sodium chloride crystallization. This is my point, and you can see from about 1103 liters, the volume has gone down to 124 liters. So more than 90% of the water has evaporated. Why? Because my saturation solubility point of sodium chloride is something like 26%. So obviously I have to evaporate very large amounts of water to reach the saturation point. Once I reach the saturation point and I continue to evaporate, what happens is that my sodium chloride will keep coming out. But because the sodium chloride solubility does not change very significantly, what you'll find is that you maintain a more or less a constant Bombay for quite some time. Like for example, you might say is going from 2.8 to 24, but no salt came out. Whereas when I go from 24 to 26 or 27 or 28, something like 80% of my salt might have come out. But my Bombay did not change much simply because I evaporated water and also salt came out. So the two are basically balancing each other out. What you can also see is if you compare the water balance, 1091 kg of water or liter of water is present here. Okay, and when I go to the end point of salt crystallization, this is the point where I'll usually stop. I will not try to recover any more sodium chloride. Now you can see, just work out what percentage of the water had evaporated.
So 96.8%.
96.8%.
Right.
96.8.
Around 97%. Okay. So you can see that how much water had to be evaporated. 97%. Of course, to the extent that small amounts of water will be contained in your gypsum as 2H2O, and some of the salts also may be hydrated. There will be some amount of moisture in sodium chloride, So everything is not that, but it is close to about 97%. And that whole thing is being done by solar energy. You can work out at home that if I had something like 30 grams per liter of NaCl in my seawater, and if I have to produce 35 million tons of NaCl, which is what India produces, how much water had to be evaporated? And if I have to do that in by forced evaporation, by providing energy from coal or something, go and figure out how much of coal would be required to do that. You'll see everybody talking about, oh, photovoltaic this, that. They forget all the things which use just solar thermal energy and how much energy you're saving. How much energy are you saving when you're drying your clothes in the sun outside? Your clothes will have something like 30% of moisture after they come out from the washing machine. And go and find out 1.4 billion people, how much clothes are washed every day and how much solar energy is being used to dry your clothes. And same is true for this. So these are all the unaccounted uses of solar energy. It's an incredible thing which people seem to forget about. Another point which I want you to make a note of is that you can see that you're starting with something like, say, 30 kilograms of salt, NaCl, in this volume, and later on you're ending with about 7, means that something around 76-77% NaCl is all you're recovering. You're not recovering all 100%. Keep that in mind also. Let me ask you that besides solar energy, of course we talked about solar energy, what would be some of the other factors which will be important and which will affect the productivity of making salt?
Sir, clear weather.
Clear weather. What is clear weather? What do you mean by that?
Sir, if it's cloudy, then the solar energy wouldn't be available for the
So, yeah. Clear weather. Okay.
So concentration of the seawater.
Wonderful.
So humidity.
Humidity. Wonderful.
availability of labor for raking.
Availability of
Labor for raking the salt. pans.
labor. Then
Transportation.
Time taken in production. It is a very slow process.
time taken is more, but time taken will depend on land requirement and this that. No, I can spread it over a larger area, right?
Yes, sir.
So indirectly, that land requirement and time taken are linked.
Separation processes.
Separation process. You mean this will affect the salt production rate? Okay, let's put it down. What else do I need apart from sun?
The temperature.
Temperature. Ambient temperature.
So there should be enough wind.
So seawater.
Wow, very good.
So availability of seawater also, like we
Yes,
cannot use fresh
availability
water.
of seawater or other brine, right?
Yes, sir.
What else?
So non-porous land.
Wonderful. I was hoping somebody will say non-porous land means percolation issues, right?
Yes, sir.
Imagine you are producing all this evaporating and half of it is going under the ground. So that would be a serious problem. I think you have done a great job. Let me also tell you a few factors which you have not taken into account. Like, for example, you'll have to also look at the logistics of how you bring in seawater and how, for example, when it goes into these various pans, how do you think it will go and how will you bring in seawater? What would be the best thing to do to bring in seawater?
So using the pump.
Using pump? Anything smarter?
So using the tides and creating grids.
Yes. Why not tides? And remember, just like I told you, solar energy, that people forget all the informal work that gets done by solar energy. And when people are talking about this many gigawatt of power, as if that's the only thing we use solar energy for. So likewise, if you talk about all this hi-fi thing, tidal energy, this, that, all sophisticated, costly equipment, all with a view to generating power. Power is not the only thing. I'm just using the sheer force of the tide to bring in water into my salt works. And so that's another thing that you would prefer, to set up your salt places where there is a good tidal action and things can be brought in. And once the tides are bring in the water, then you lock the gates and prevent the water from going out. And what would you do to move it from pan to pan?
Creating channels or canals.
Create channels of create channels. And how would they flow?
Use a bit of slope, like the land should be a bit sloping.
Yes, create channels and have a slope. In other words, do contour mapping. Understood? Huh? And the smartest thing to do would be to force the seawater into the place where it is at a maximum height. Okay? And from there, just feed it by gravity all the way down. If you didn't do all these smart things, your salt would cost a fortune. So I hope you can see what are practical things in producing salt. Is it all clear?
Yes, sir.
And I am very happy. I'll just put students. Another thing that you must remember, and you did mention about humidity, and weather, of course, plays a very crucial role. Like, for example, in Gujarat, and Mumbai, we have salt works in Vadala, some places in Mulund. In fact, Bombay used to produce much more salt before. I used to see many more pans before, but because real estate is so costly here, so all these salt works are slowly disappearing. And another reason is because the productivity of salt production is lower here because of weather factors, etc., as compared to a more semi-arid place like Gujarat. And that's why, those guys produce about 80% of the salt in our country.
So does the brine quality also get affected over here?
Yes, it gets affected here, but it gets affected even in Gujarat because of all the anthropogenic activity, all the boats, ships, this, that, pollution. You have all these factories. You have impurities coming from all of this. In fact, at some point, we'll have to be worried, like if you're making edible salt and if all these junk is present in the seawater, who knows, whether the salt is good enough to eat, because you don't really give that much of a treatment subsequently. You just trust the seawater is safe and you make the salt and you consume that salt. A lot of the salt is produced that way, not all. Okay. Now, another thing that you need to note, you remember I told you about water activity. Water activity is linked to vapor pressure. If your relative humidity in a place is such that my relative humidity I can express as P by P0, and that is again related to A by A0. So what happens is that if my relative humidity is very high, I cannot evaporate beyond a point. I may not be able to even produce salt under a very humid condition. I know that some of you talked about clear weather, humidity, absolutely. But you need to quantify it. And just to give you an idea that where you are producing salt, say some point like where, this is the density, Bombay. Okay, so we produce salt till about here, okay, around here. So here you can see that the relative humidity will be around, say, 65%. Means if you have got a place where the relative humidity is more than 65%, then you cannot make NaCl. You can make it only in a certain percentage. And this is the onset of salt crystallization, this point. Okay, and that's about 70%. So if your humidity is more than 70%, don't even bother to try and make salt. It'll never happen. Is that clear?
Yes, sir.
I hope you understand the importance of all this.
Sir, one doubt.
Yeah.
So if we say that the humidity should be around 60%, isn't
Yeah.
that a contrast in where we are getting the brine and where we have to dry it? Like it should be far enough because
No, your salt pans will always be right next to the sea coast. When I say sea coast means you'll probably be a few kilometers away, because it's not as if the tide is directly coming. There will be you will have some channels from the sea, coming up to your salt works, and you have to look at the relative humidity at that point. Okay,
okay, sir.
Thank you, sir.
thank you.